For lecture 7, we began with a review of Monte Carlo integration. So suppose we have random variable x follow a probability density function f of x, and then we define expectation for a function of random variable x to be the integral of hx fx dx. So here, this is a capital X standing for the random variable, and here this lowercase x standing for the random variable for this integral. And we write this as I. I stands for integration. And then Monte Carlo integration means that we can draw random samples, say x1, x2 to xn from f of x independently and identically distributed. So that's IID stands for independent and identically distributed for those random variables. Then we can approximate this integral I by I hat. So we put hat on top of I, indicating that this is a estimate for this unknown constant I. And it is computed as the sample average for h for xi that you sampled from this density. So that is, we use this sample average I hat as a estimate for this Monte Carlo integral. So a special case is that h of x is an indicator function, so that it is 1 if x is in this set A and 0 otherwise. And for this integral, which is expectation for this special h, the indicator function, so we can write this as the integral of the indicator function fx dx. So therefore, we only need to compute the integration of f within the range of A, which in the one-dimensional case is the area under this curve within this A. Okay, so this shaded area, and this is a probability. So that is the expected value of indicator function is probability. And we then approximate this probability by the sample average. And in this case, the sample average for this indicator function is simply the frequency, how often this xi belong to A. So that is, we approximate or estimate the probability by the frequency. Because if we look at the sum, so this simply count the number of times that xi fall into A, and we divide this by the total number of trials, we get this frequency. And the above formulation appear to be a little bit abstract. So here I want to again emphasize the intuition. That is, we have a big, effectively almost infinite, large population, and the distribution for the points in the population can be described by a density function as a mathematical idealization. And then this unknown constant I, this integral of the expectation, can then be interpreted as the population average. For example, we have a population of 300 million people, and we look at the population average. And this population is described by the density. So when we say we draw IID, independent and identically distributed samples from this density, it is like we just randomly sample n points from this population repeatedly. So each time we randomly sample 1 point from this population, and we repeat the same sampling process n times. So we get n points. So we get a sample of n points from this population. For example, we get 1,000 people from this population of 300 million people. And then we have this sample average. So the sample average, we just look at the average of h of xi, right? So this gives us the sample average. And we use the sample average to estimate the population average. So this is intuitively very easy to understand. So the key point is that if we idealize the dense distribution of the population of the points by a density function, then the population average can then be written as an integral, which is the expectation. Okay, so that the integral is really a mathematical idealization for the population average. That's why we can use a sample average to approximate or estimate the population average. And in the special case where the h function is indicator function, so in that case, then we know that the average of the indicator function simply become the frequency or the sample proportion. And similarly, the average for the indicator function over the whole population becomes the population proportion. And then under random sampling, according to axiom 0, then population proportion becomes the probability. And that's why we estimate probability by the frequency. And in this framework, it is worth of knowing that the population average or population proportion, which can be written as an integral, is fixed but unknown. And then for this sample average or sample proportion or sample frequency, so they are computed based on the random sample, which means if we repeat this process again, we are going to get a different sample because of the randomness. Therefore, the sample average is random. So when we put a hat on top of I, this I hat itself is actually random, or it is a random variable. So that's the basic concept. So if you look at the example for estimating pi that we studied last time, so we have this unit square, and then we have this 1/4 of the circle on this positive range where x squared plus y squared equals 1. And for this example, so the expectation of this indicator function that the random point fall below this curve, or in other words, it fall into A, would be simply just the integral, right? The integral of this unit square of this indicator function of dx dy. And this is simply just this area, the area for this A, which is a probability that x squared plus y squared less than or equal to 1. So the expectation is a probability as we derived before, and this probability is simply the area of A divided by the area of omega, and the area of omega is 1. The area of A is pi over 4. So this is a unknown concept. Supposedly, we don't know pi, although we define pi to be the area for the unit disk, and this is 1/4 of the unit disk. So that's why it is pi over 4. So even though we can define pi this way, supposedly we don't know how to compute pi. So therefore, we can use Monte Carlo method. So that is, we randomly sample points x, y. So this is a single random point from the uniform distribution over the unit square. And then the probability that the random point belong to this A is pi over 4, as we derived here. And then we can approximate this expectation or this probability by the sample average or sample proportion. In other words, we can sample IID points, independent, identically distributed points in the from the uniform distribution over this unit square. Suppose we do this 10,000 times, and then we approximate the integral by this I hat, which is the average of these indicator functions, which actually count how often the random point fall into A. And here, the summation of those indicator functions count how many times the random points. So here, xi, yi, this is actually I, right? Not 1, xi, yi. So how often this point fall into this A, and the summation is m. It should be here. This summation of those indicator functions actually counts how many times the random point xi squared and yi squared fall into A. And if you divide this by n, you get the frequency. So let's call this a summation be m. So m over n is the frequency of sample proportion. So intuitively, if you randomly throw a lot of points into this unit square, say m equal 10,000, and you count how many points fall into this A, this 1/4 of the disk, and then you get pi hat. You get the pi over 4. So m over n is actually pi over 4. And from here, you can then estimate pi by this pi hat, which is 4m over n. So even if you fix n, m can be different, right? So if you do it again, you are going to get a different m. So m is random, and this pi hat is also a random estimate. So in general, pi hat being a sample average or sample proportion can change from time to time, right? You repeat the experiment, you are going to get a different number. But the hope is that on average, this number is our unknown constant. Or in other words, this I hat as a random variable itself fluctuate around the true unknown constant I. And certainly we hope that this I hat is accurate, where the accuracy can be measured by the variance of this I hat. So that is, suppose we repeat the experiment a lot of times, or in other words, suppose each one of you in this class perform the same experiments, throw 10,000 points into the unit square and count how many times it fall below this curve. And then each one of you will get I hat. So if I do a scatter plot for all the I hat you get, hopefully it fluctuates around the true unknown constant I. And hopefully the magnitude of the fluctuation, which can be measured by the variance, or you can also take square root to get the standard deviation because the variance is on the square unit. In any case, so hopefully this fluctuation is small. The magnitude of the fluctuation is small. So this is a statistical paradigm for estimation. And in fact, statistics is really about this matter. So you have an underlying population, either a real population or a more abstract density, and you have a finite number of usually independent and identically distributed observations or samples or examples from this population, and you want to estimate something about the population so that you can generalize to the whole population. So this is the idea of statistics and learning. And here we just use the sample average to approximate the population average in this Monte Carlo study. Later, we shall actually derive the expectation for I hat and the variance of I hat more rigorously. But before doing that, we want to be as concrete as possible. So let's look at some concrete examples where we want to develop different Monte Carlo methods for the purpose of reducing the variance or the variance reduction. And we still want to continue this example of estimating the pi, and we showcase a few tricks or a few methods so that we can reduce the variance. So one method is called conditioning. So the idea of conditioning is as follows. So suppose we generate x squared and we generate this x and y as a random point in this omega. We randomly throw a point into this omega and let xy be the position for this point. And then our pi is the expectation for this indicator function for x squared plus y squared less than or equal to 1. That is the probability that the point fall below this curve. And if we look at a fixed x, okay, we look at the fixed x, and suppose we look at the vertical slice from x to x plus delta x is infinitesimally small. And if we look at how often within this vertical slice, how often the point fall below this curve for fixed x, and we know that this probability is simply the square root of 1 minus x squared, because the height here is square root of 1 minus x squared. Since x squared plus y squared equals 1, and fixed x, we know that y equals square root of 1 minus x squared. So the height is square root of 1 minus x squared. So the probability that a random point fall below this curve, given that the x coordinate of this random point equal to this small x, is this quantity. Okay, so therefore, we know this probability in closed form. So we don't need the variability. So if you randomly throw 10,000 points into the unit square, and if you look at all the points in this vertical slice, then the proportion of the points fall below this curve may fluctuate around this number. You don't want this fluctuation, so that you want to reduce the variance. So the point is, if you can compute anything deterministically, you never want to use Monte Carlo method to introduce the randomness or the noise. Okay, so avoid the Monte Carlo method whenever you can use a deterministic method to do the calculation. So therefore, we just want to calculate, or we rewrite this integral, which is the expectation, because the expectation is the probability, right? So if you look at this probability, and for this one, so if you look at because the probability is like the long run frequency for the points fall below this curve, right? And if you look at what's the frequency or the proportion for the points here, this proportion is actually is the area of this small vertical slice, right? Which is delta x times 1 delta x. So that's a delta x. And among those delta x points, then the proportion of the points below this curve is square root of 1 minus x squared. So therefore, if you look at this small area is square root of 1 minus x squared times delta x. And then we compute the integral for this area. We sum over all the small bins, we get the total area, right? So that's how we write this one. So the way we write this is that we now can use Monte Carlo method to approximate this integral directly instead of computing the double integral over both x and y. Or in other words, we want to eliminate the randomness in y by conditioning on x. Okay, so that's a basic idea. So after rewriting I only in terms of x, because we basically integrate out the y. Which means we do not need Monte Carlo method for computing the inner integral for dy. We can compute it in a closed form. So therefore, we only need to calculate the integral over x, and this is integral for this function. Now this becomes our h of x, okay, h of x, and our f of x is 1 for x within 0 to 1, because this uniform distribution within this interval. So therefore, we just randomly sample x1 to xn IID from uniform 0, 1, and we don't need to sample y anymore, because we know the probability that the y below this curve is this one for any fixed x. And then we use Monte Carlo method to approximate this integral where h of x is this function, and f of x equals 1 within this range. So we can then approximate the integral I by I hat, which is the sample average of this function value. And this gave us another Monte Carlo estimate. And hopefully this one has a lower variance or more accurate than the previous one, where we simply count m over n, right? So this is the idea for conditioning, which means if you condition on x, you can integrate out y. You do not need Monte Carlo method to do the integration over y. And this way, you get rid of the randomness caused by y. Okay. So this is the first method for conditioning. And later, we shall focus on this integral, okay, which we get rid of y so that it has hopefully a smaller variance. So in the homework, you can actually check the variance. And another method, we continue to use this integration. So the integral of square root of 1 minus x squared. And we can continue to reduce the variance by the so-called control variate, not control variance, control variate method. In other words, we subtract a contrast. So the idea is that if we look at this triangle, the area of this triangle is 1/2, right? And so therefore, we only need to compute this part of the integral. So that is 1/2 plus the area of this part, which is the integral of square root of 1 minus x squared minus 1 minus x. So here, this line is y equals 1 minus x. We look at the difference. Okay, and therefore, our h of x now become this function. And the fluctuation for the difference is reasonably small compared to the fluctuation of this whole curve over this the height, right? The height of this curve. So you have a contrast or some cancellation, and then again, fx is 1 for the uniform distribution. Okay, and then we can write this I as 1/2 plus expectation of now this function f of x, right? And then we can approximate this I to be 1/2 plus we use Monte Carlo method to approximate this this integral or expectation so that we get summation of square root of 1 minus xi squared minus 1 minus xi. So this is a Monte Carlo approximation to this integral. Okay, and this is a control variant. Basically, you just still follow the same principle. That is, if you can compute the integral deterministically, like this function, then you don't need to compute it using Monte Carlo method. So what you do, you just get 1/2, and then you subtract it. Okay, and this one and this one, both actually you see the same trend. If this is above average, then this tends to be above its own average. And if this is above its average, then this is if this below average, then this also tends to be below its own average. So they seem to change together. So therefore, by subtracting this one, you actually cancel some of the variation. So this is a very important variance reduction scheme. Okay, another method is called antistatic variable method. So this is based on the observation that if xi follow the uniform distribution, then 1 minus xi also follow a uniform distribution. So therefore, when you generate xi, you can also use 1 minus xi as another sample. So that is now you have both xi and 1 minus xi as a random sample, and when you sample n copies for xi, ID copies, then you also have another n copies of 1 minus xi. So in total, you have 2 n copies. And you look at the average for the function value of these 2n random samples. So that is summation over I from 1 to n, and then this is square root of 1 minus xi, and then this square root of 1 minus xi, another sample. The point is that if one is above average, then the other tends to be below average. So therefore, if you sum them over, again, they cancel the randomness, as we will formally show later on. Okay, so this is the antistatic variable method. Now let me introduce yet another method called stratified sampling method. So this method is based on the observation that suppose you sample a lot of points within 0 to 1, right? Those xi. And then if you count the number of points in this range, number of points in this range, number of points in this range, they can be different. For example, there may be 90 points here. Suppose you sample 300 points. There may be 90 points here, 80 points here, 130 points here. So in the total, you have 300 points. But if you want to avoid the fluctuation in this number, supposedly you should have 100 points here, 100 points here, 100 points here. So this is idea of stratified sampling. So you just control the number of points in each interval. You use the expected number so that you can reduce the fluctuation. For example, if we really implement this idea, we may divide the range of 0 to 1 into 10 intervals. And you sample 1,000 values in the first interval, another 1,000 values in the second interval, and keep doing until you get 10,000 points over the whole interval. So you have 1,000 points within each interval. And then you can calculate the average of this 1,000 points. So this is called the stratified sampling because we divide the range from 0 to 1 into 10 strata, and then we sample equal number of points within each strata. So this actually this method is also used in the real survey sampling. Okay, so these are just some examples for doing Monte Carlo methods to reduce the fluctuation or reduce the variance. So now, in order to study this more formally, so I want to give you some background on probability theory. So I don't want to just make this course as a course of probability theory. Rather, I just provide the necessary background whenever necessary. So here, our goal is to analyze the Monte Carlo methods, in particular, the expectation of I hat and the variance of I hat. For that purpose, we need some background on probability theory. And again, I want to do it in an intuitive way. So we start from this multivariate density. For example, we have a population, and in this population, we let x to be the height, y to be the weight, so that each person become a point according to their height and weight. And then we plot 300 million points. We have a point cloud. And this point cloud can be mathematically idealized as a density function. So that is, if you look at a small range, x to x plus delta x, say 6 feet, 6 feet, 1 inch, and another small range, y plus delta y, so this, say 160 pound, 161 pound. Look at this range, so they cross a small cell. And then let's assume that we have a population of n points, where n is almost infinite. So here, those points are 2D. So each one is described by 2 coordinates. And we let nxy to be the number of the points in this, this small cell, which is x plus delta x cross y plus delta y. And then we can define the density as this nxy, the number of points, divided by the size of this cell, which is area, right? Delta x times delta y. And we also want to normalize this number by the total number so that we divide this nxy by n so that we count what the proportion of the whole population belong to this small cell. And then we divide this proportion by delta x, delta y. So this gave us the population density. At this point, there is nothing random at all, right? But if we randomly sample a point from this population of the points, then the probability that the sampled point fall into this small cell become the population proportion, which is nxy divided by n, according to axiom 0, because all the points are equally likely, right? So here, then you see that this population proportion now has a probabilistic interpretation under uniform equal likely random sampling. And then now we can interpret this f of xi as a probability density function, because now this population proportion become probability under random sampling. Okay, so then we have this density function, which is a probability that random points fall into this cell divided by the area of this cell. And here it is like we smear the probability mass on this cell uniformly within this cell. And if delta x and delta y are infinitesimally small as a mathematical idealization, then we get this notion of density, which is a continuous function. And from this density idealization, we can now compute population average for a function h for xi, yi. So we let I goes from 1 to, this should be capital N. So this is 1 over capital N. This summation is I from 1 to capital N. We look at the population average. And then you can actually go over all those cells, x plus delta x, y plus delta y, the cells that we see in the previous slide. And then we have this hxy. For all the points belong to this cell, we know that the values are essentially all the xi equal to x, and all the yi equal to y, subject to this infinitesimal small range delta x, delta y, right? And then the number of points in this cell is nxy, and here you divide this by n, so this give you the population proportion, and this population proportion is also the probability and the random sampling, right? And this is exactly fxy delta x delta y. So this density times error gave us the probability of population proportion, which is here. And then you have this summation. And if you let delta x, delta y to be infinitesimally small, then this summation becomes the integral for this hxy and fxi. Here, this delta x, delta y become dxdy in this integration notation. And this is a population average, which we define as, or we denote as expectation of h of xy. So capital X and capital Y indicate a random point follow this density, or a random point draw from this population for points. So this is expectation, and it can be written as an integral, as a mathematical idealization. And this is just a simple generalization of what we studied about the expectation from the one-dimensional situation to the two-dimensional situation. Okay, and this actually gave us the foundation to study a special case. So that is for h of xy to be just x plus y. This is a special case that enables us to analyze the mean and the variance, expectation and the variance for this I hat, because I hat is like the summation divided by the sample size n, right, small n. And here we study the statistical property of x plus y. So we know that the E of x plus y equal to EX plus EY, because E is population average. We average over all the population, all the points. And this can be done by first average or x, right? You look at the average of x, and then look at average of y, and then you sum them over, you get the average of x plus y. Or in other words, average of the sum of xy is the sum of average of x and average y. So this part is easy to understand, but the variance become a little bit tricky. So variance of x plus y, this is expectation of the population average of x plus y minus the expected value of x plus y, which is ex plus ey, and then you square it. So this is how we define the variance, which is the population average of squared deviation from the center. And we can then regroup this into x minus ex plus y minus ey, and then you square it. So now you have the square of the summation of two terms. And then you get the square of the first term plus the square of the second term, and plus 2 times the first term times the second term. And then you compute the population average. We know that the expectation of this one, the population average of x minus ex, this is the variance of x, and the expectation of y minus ey becomes the variance of y, and the expectation of this one, this we need a new notation. This 2 times covariance xy, where the covariance of xy is defined as the expectation of x minus ex, y minus ey. So we want to know how xy change together. That's why it is called covariance. And if you look at this quantity, This is again the sample average of x minus ex, y minus ey, and ex, ey are the sample averages of x and y respectively. So still, let's look at this cloud of points for the whole population. So let this be ex, this be ey. So this point is the center of this data cloud. And then we can divide the whole range into 4 quadrants. So this region 1, region 2, region 3, region 4. For this one, x minus ex is bigger than 0, y minus ey is bigger than 0, so their product is positive. And for this one, x minus ex is less than 0, y minus ey is bigger than 0, so their product is negative. And similarly for this one, x minus ex less than 0, y minus ey is less than 0, so negative, negative, their product is positive. And for this one, it's negative. So you can think of those people are big people, right? Those are the small people. And those are skinny ones. Those are the opposite. And if there's a positive trend, you see that there's more points in 1 and 3, which give us positive product than the points in 2 and 4, which give us a negative product. So in that case, the covariance between x, y are positive. Okay, so this is example of positive covariance. What about the negative covariance? Okay, so in this case, covariance is positive. How about the negative covariance? So the negative covariance is like here. So you have this type of plot, but this time, if we continue to let y to be the weight, then x cannot be height, right? It doesn't make sense if you increase the height, the weight decrease. So you may change the height of x to another variable. For example, how much exercise you do every day or every week. So if you spend more time, this is time that we spend on exercise. So if you spend more time, hopefully you lose some weight. Okay, and in that case, by the same logic, if you divide this data into 4 quadrants, 1, 2, 3, 4, and here the product are positive, here the product are negative. But this time, for this data with negative trend, you actually see more points in the negative quadrant than the positive ones. So therefore, for this one, covariance is less than 0. So therefore, the sign of the covariance measures whether there's a positive trend or the negative trend. Okay, so if you now let's look at the situation for the variance of x plus y. So we know that the variance of x plus y equal to variance of x plus variance of y plus 2 times covariance of xy, right? So now if you again look at the population of n points, say n is 300 million, and then imagine that you want to know the marginal distribution for x. So you can shed light and project all the points into the y-axis. And then you get 300 million points on this y-axis, right? And then you get the density, the notion of density. Similarly, you can project the points onto the x-axis, and then you get the marginal density of x because you have 300 million points distributed on x, from which you can then get the density as a mathematical description. Okay, so this is marginal distribution. And now, if you look at the variance for x plus y, then what do we mean by the distribution of x plus y? So the distribution of x plus y can be seen by shedding the light in this direction. The reason is that if, say, there's a point which is x and y, then if you look at this line is x plus y equals constant. And then this become like x plus y and 0. So the horizontal coordinate become x plus y, and vertical coordinate becomes 0. And this point is 0, x plus y. The horizontal coordinate is 0, and vertical coordinate is x plus y. So that is, you can project in either this direction or in this direction, and you get the points. You get a lot of points. And if the point is that the intuition is that if you look at the 2D points, there's a point cloud. So here you see a positive trend. so covariance is bigger than 0. And if you shed light in this direction, you get those points, and they are more spread out. So the variance is big. So that is, you add 2 times covariance of x and y with positive covariance. In the case of negative covariance, you have this type of shape, and the marginal distribution may still be the same. If you project to x or project to y, you see the same thing as here. But if you look at this direction, x plus y, then it is more focused, right? So that is, the variance becomes smaller because of the negative covariance. Because the variance of x plus y, you need to add 2 times covariance of x and y. And in this case, covariance is negative. So if x is above average, then y tends to be below average. So they cancel each other. Okay, so that's the idea for negative covariance. And in Monte Carlo method, we actually try to introduce negative covariance, and then so that we can reduce the variance. So this is idea for antistatic variable, where we introduce negative covariance, or in this idea for cancellation or subtracting a contrast, that's also make the covariance to be negative, right? So, for example, in this case, when we subtract something, for example, the variance x minus y, right? So that will be variance x plus variance negative y, which is the same as the variance of y, and then plus 2 times covariance of x and the negative y, which is a negative covariance xy. So that is, if y and x are positively correlated, but you have negative sign here, you do the cancellation, then you reduce the variance. So that's the idea. It is still based on the same formula that we derived before. So both antistatic variable or the contrast of this control variate are based on the idea of reduce the variance. Okay, so antistatic, you have this one variable plus another variable, and they have negative covariance. And for the control variate, you subtract this y. So if y and x are correlated positively, have positive covariance, then we reduce the variance because of this formula. Okay. So this is just the basic idea for this variance and variance reduction. So if x and y are independent, which is relevant in our study of Monte Carlo samples, because all our samples are IID independent and identically distributed. So if that's the case, then we have this scenario. So we have a collection values of x. Say, suppose we have, say, n points. So very big n points for x, and we have a population of n points for y. And then xy can be considered all those points that crossed. So you, for each x point, you erect a vertical line. For each y point, you have a horizontal line, and you have cross, right? And you look at all the points crossed. So those can be considered as the population of xy, where x follow a density f of x, y follow another density g of y. So f of x is a mathematical description of this n capital a population of capital N points, and the g of y is a mathematical description of a population of n points on the y-axis, and both m and n are effectively infinite, and then you have m times n pairs, and those are the points. This form a population for the points that we have this xy, right? The points of xy. And for that independent type of scenario, covariance of xy equal to 0. So that the variance of x, sorry, this variance x plus y, variance x plus y equal to variance x plus variance y. The reason covariance xy equal to 0 is that we know the covariance xy equal to the sample of the population average of x minus ex, y minus ey. So when we compute this, so suppose we can first fix x. So for each x, if you look at this distribution y, they are all the same. For different x, you have the same distribution of y. So that's another notion or another way of understanding independence. With this cross, this become quite obvious, right? At each x, the distribution y is the same. And then you can actually just look at because now you can just look at the expectation y minus ey, right? So that is for a fixed x, this is a constant, and you look at the expectation y minus e of y, they are all the same, and the same distribution as the marginal distribution of y, and this quantity is actually 0. Okay, so therefore, if you then average over all x, you still get 0. So the point is that under the independence for each fixed x, the distribution of y is the same as the marginal distribution. And then you can compute the expectation for the marginal distribution y minus e of y. So you get 0, okay? Because that will be e of y minus e of y. This is a constant. You get 0. So the covariance is equal to 0. And also, it means that there's no trend whatsoever in this situation, right? You don't see any positive or negative trend in this type of pairing. So in that case, if x and y are independent, then covariance of xy equal to 0. Actually, the reverse may not be true. So if the covariance equal to 0, that only means there's no linear trend, but there may be perfect nonlinear trend. However, the forward direction is always true. So if x and y are independent, then covariance of x and y equal to 0. Okay, so in that case, then we have this variance of sum equal to sum of variance. Okay, so that's a very important result that enable us to then study the IID samples. So suppose we have x1, x2 to xn, they all follow f of x and they are independent. And let's assume the expectation of each of xi equal to mu and the variance of xi equal to sigma squared. So that is mu is a population average and sigma squared is a population variance. And suppose we look at the summation of those values. So we know that the expectation of sum is the sum of expectation, and the expectation of each one is mu. So the expectation of sum is n times mu. And similarly, variance of sum equal to sum of the variance because they are independent. There's no covariance. Covariance equal to 0. So therefore, since the variance of each term equal to sigma squared, and the variance of sum is n times sigma squared. And then we look at the important quantity, that is x bar equal to the summation divided by n. So this is a sample average. And then E of x bar will be the expectation of S divided by n, which is mu. But the variance of x bar is expectation, a variance of S divided by n squared. Because if we divide S by n, we need to divide the variance of S by n squared because variance is the squared deviation from the mean. Okay, so therefore we need to divide this variance of S, which is n sigma squared, by n squared. So this gives us sigma squared divided by n. So this is an important quantity, which means that if we look at the sample average x bar, it is still random because of the randomness in random sampling. But this x bar fluctuates around mu, and the variance of x bar decrease proportionally, inverse proportionally to n. So by the same logic, then this I hat, which is a sample average for h of xi. So we can prove that the expected value of I hat equal to I, that is I hat fluctuate around the unknown constant I. This means that I hat is unbiased estimate of I. So we don't introduce systematic bias by using Monte Carlo method. And similar to this result, this sigma is a variance of each of xi, right? And now I hat is the average of h of xi. So we only need to change sigma squared to variance of h of x, where x is a single random variable. And then variance I hat is a variance of h of x divided by n. So this is n, not h, this n. So that is the variance of I hat, or in other words, the magnitude of the fluctuation is inverse proportional to the sample size n. And it has nothing to do with the dimensionality of x. So that means the Monte Carlo method actually avoid the curse of dimensionality as long as you can do random sample. You can draw a fair sample from the density f of x. Okay, so this here, the logical flow is that we look at the expectation and the variance of x plus y. And in the independent case, the covariance of xy becomes 0. And then we can derive this result and then generalize this to h of x. We get that our Monte Carlo estimate I hat is unbiased, fluctuate around I, and the magnitude of the fluctuation, that is a variance of I hat, is a variance of h of x. X is a single copy of the random variable follow f of x divided by n, the sample size. Okay, so I think in the next lecture, we will come back to this point with a little bit more details and depths, and then we move on to study more sophisticated Monte Carlo integration.